Thank you, Mr. Chairman, for introducing my paper. Good afternoon, ladies and gentlemen. My contribution is named the Dual Core Plus Gradiometer with gradient feedback, and as you heard, I'm with the Czech University in Prague. I will start off with some very basic introduction, so I will go very fast through it. What is a magnetic field gradiometer? Either you can measure the whole 3x3 9-component magnetic sensor, but mostly you can be happy even with the axial gradient, which is the diagonal component of the central matrix. It makes really sense to measure magnetic gradient because if you take a look at the dipole source field profile resistance, you will see that the magnetic field changes very rapidly at the beginning. How do you measure the actual magnetic gradient? You just take your two magnetic sensors, put them in a distance d, and okay, that's how this works. Never mind. And it's only approximation of the gradient, and the approximation is better as the distance is lower. If you want to be non-cryogenic and still keep low noise, finally you end up with AMRs or with Fluxgate. And the reason why to measure the gradient, for example, you wanted to suppress the magnetic disturbances, which can be far and is homogeneous. You want to detect the response of your object in either DC or AC induced by eddy currents, and you want to measure in a noisy environment. And or you just want to use the gradient as a value, for example, for calculating the position or of the dipole, force, strength, etc. And let's take a look at the basic gradiometer configurations you can create to measure the actual gradient. The very classic one is just take two magnetometers in feedback loop, place them in some reasonable distance. The problem is they should not influence each other by the feedback, which cancels the measured field. And you can end up with very low noise gradiometer if you increase your distance, for example, to half a meter, which is reasonable. If you put two triaxial sensors, you would be able also to compensate for any geometric error, because you can always recalculate the matrices on the non-perpendicularities of the sensor head. But the basic problem is you have large demands on your data acquisition because you are hunting for the last few bits of the measured voltage. One way how to overcome those drawbacks is to create so-called single core gradiometer. This is the one magnetic core of the Fluxgate, and you use two pickup coils in resistance. The problem is you have to run it in an open loop, so you end up with stability problems, with drifting time, etc. And then there is a problem with the correlation of the noise from the core. We have tried this approach also, so we know about those problems. And finally, we end up with dual core gradiometer with gradient feedback, which is the name of the talk. Basically, you have your two sensors, and you measure both gradient and homogeneous field in a feedback loop. You can place your feedback coils in the grooves here. And because also the information about homogeneous field is available, you can then easily correct for geometric errors. The drawbacks are, of course, complexity, and the geometric errors, if you don't compensate, are very large. I will show later. Some quick characterization of the sensors we have used. Because the gradient base is low, also the Fluxgate sensors should be miniaturized. Of course, it's not microns, it's not millimeters. In Fluxgate, even 10 millimeters is enough to say it's miniature. The sensors are composed of amorphous tape, which is wound on the ceramic bobbin, and finally the sensor is constructed looks like that, with a pickup coil on that. And the problem is with these small dimensions already the bending stress starts to play a role. So suitable magnetic field annealing should be done, and finally you could end up with such nice PhD as shown here. So what's the principle of the operation of the gradiometer? You can see the two Fluxgate sensors here, and we have got two independent signal detection electronics here connected to the respective sensor. And what you do is to sum and differentiate those two signals, and you have two feedback loops. And this comes as an error signal to the feedback loop, and you have your homogeneous coil, which is the bold one here, and your gradient coil, which is the special one in gray here. And you can compensate both for the gradient and both for the homogeneous part of the field. Of course, the gradient coil has to be specially created to create pure gradients and not to generate a homogeneous field, and the same for the homogeneous coil. And how does the sensor head look like? This is before the coils were wound on it. So you can see the grooves here, and this is the two Fluxgate sensors in the axial direction, the coil. If you wind the coils on that, you can see the alternating orange and green here. Orange one is for the homogeneous one, and the green one is for the gradient. And there is also a nice X-ray picture, you can see how does this look like. Of course, the number of turns has to be optimized to obtain a clean profile of gradient and homogeneous field, and we did it in some 3D FEM simulation. And the problem with the small gradient base, with the small distance of the two sensors, is that even very low tilt of this sensor can induce gross errors when measuring the gradient. The other problem is that if the homogeneous coil has any imperfections and there is a position asymmetry of the two cores, you end up also with another parasitic gradient response. So we can divide it into two parasitic parts. One is dependent linearly on the homogeneous field. The other one looks like more complicated because it does not depend only on the tail, it also depends on the angle to the vector you are measuring. But this is a vector of the Earth's field, and on this vector there is superimposed very small gradient. And then when you are measuring, you just take your sensor head and you rotate it in the Earth's field, which is the standard way how to say whether your gradiometer is working well. You could end up with the red response here, which is very similar to the homogeneous response. If you apply the first correction, with this first coefficient you can measure, for example, in Helmholtz coils, and you can see that it's pretty linear. You end up with the blue. And if you apply also the second correction for the tilt, either you can measure the tilt by some theodolite, or you can just try to fit your equation. You could end up with this response, which is pretty reasonable. That previously was done just making those movements in some public park. We didn't know about the gradient there, so we went to a magnetic observatory where we could measure the DC gradient, and it was less than 2 nanoteslahs per meter. It was measured by Overhauser gradiometer. And the angle to the Earth's magnetic field was estimated by the magnetic field value, which we could measure with the Overhauser. So again, you can see this is the effect of movements in horizontal plane. This is without compensation, first compensation, the second one. It's almost a clean signal. Of course, one would say, how can you know the angle to the field you are measuring, to the vector? For the Earth field, it's easy because you can estimate your Earth field value, and with some units of percent of error, you end up with very good compensation. Or you could just add 2 more axes to measure the 2 more perpendicular components, and you can compute the angle all the time. But in the real world, your movements would be very small, or you would make your sensor head fix it. And just to show the performance in terms of stability and peak-to-peak noise, this is not in a shield, this is in the observatory. This is 60-second record, and the peak-to-peak noise was around 20 nanometers per meter, and we could see the stability is better than 5 if you would make an average. So the stability is pretty reasonable. And the standard figure of the performance of a magnetometer or even gradiometer is to measure the noise. So we were measuring the noise in the 6-layer magnetic shield. And what we ended up with was around 1 nanotesla per meter per square of hertz noise. And the homogeneous noise was about 20 nanotesla. So this is the output of the two signal paths of the electronics. It was measured by a SST analyzer. So I have to say that this one does not have any ADC on it. It's a pure analog instrument. The homogeneous noise was a little bit large, 20 picotesla per square of hertz. It was driven mainly by the requirement of low power consumption. So we always achieve it double your power consumption. Okay. So if I conclude my talk, around 1 nanotesla per square of hertz gradiometer was presented with only 20 millimeters gradient base. We have seen that the geometric errors, which can be gross in this case, can be compensated knowing the angle to the measure factor. And either if it's a priori known in the case of the Axial, or you can calculate it from 2 additional axes, of course, that would increase the complexity of the gradiometer, adding another 2 sensors. But if the sensor head is fixed or the movement is limited, for example, if you would scan your object or if you would attach the gradiometer, you can neglect the geometric errors. Okay, so I would acknowledge the support of the friend agency, and I thank you for your attention.